Let's look at another related rate problem. This time we're going to have an angle that's changing. So an observer standing 200 meters from the launch side of a hot air balloon. Okay, so if this is where the hot air balloon was going to be launched, the hot air balloon's heading up this direction, this distance from where the observer is standing is 200. Now that's staying the same all the time. That's not changing. That person's not moving closer. He's standing 200 meters from that launch site. So go ahead and put a constant there, not a variable. The balloon is rising vertically at the rate of 4 meters per second. So the speed that this side is changing is 4 meters per second. Okay, so we're going to need a variable to represent what that length is at a given time. How fast is the angle of elevation increasing 30 seconds after the launch? Okay, we want to know how fast the angle is changing. So we're looking for the change in the angle theta. So let's look, we need some variables. We're referring to this angle, and we're referring to this vertical height, which I'm going to call y. Now both of those depend on time, because the longer that this balloon's been in the air, the higher it's going to be, and the angle's changing depending on how long it's been in the air. Okay, so both of those are functions of t. Okay, so now what do I know? What can I write the rates I'm given down using those variables? The balloon's rising vertically at the rate of 4 meters per second. That means the change in y with respect to time is 4. How fast is the angle changing? I want to find d theta dt. 30 seconds after the launch. So when t's equal to 30. Now, I may not even have a t in my equation, but I'm going to make note that t equal 30 is when I want to find that rate of change of the angle. Okay, now the 200 isn't changing, but it's going to be important in our equation, because looking at the picture, we've got a right triangle. Now, you could use Pythagorean's theorem. The only problem is we know this bottom side is 200, but the length, the person's line of sight to the balloon, we don't know anything about that. We don't know anything about a rate of change of that distance. We don't know a value for that, so we're not going to be able to use the Pythagorean's theorem for that. What we do need, though, is we need to have the angle in our equation somehow, because we want the change in the angle with respect to time. So think of how you could find an equation that relates the angle to the side there. So now Pythagorean's theorem's out, since we need to get the angle into the picture, but we can use one of our trig functions. The trig function that uses the side opposite that angle over the adjacent side, opposite over adjacent, is the tangent function. So tangent of the angle theta is going to equal to the opposite, which is the y, over the adjacent side, which is 200. Okay, so now I've got my equation. The only thing I need to do now is introduce my derivative. So I take the derivative both sides with respect to t. Remember that theta is a function of t and y is a function of t. They both depend on time. Okay, so now taking the derivative of the left side, I'm taking the derivative of a tangent function. I know the derivative of the tangent function is secant squared of that angle, theta, times the derivative of the inside. Well, the derivative of the inside, the derivative of theta, it's a function of t. I want the derivative of theta with respect to t. That's just the chain rule. Equal, now I have 1 over 200 times y. That's the same thing as 1 over 200 times y of t. So the derivative of that will be 1 over 200 times the derivative of the y, which, since it's a function of t, that's the same thing as just dy dt. Okay, so now we've got our equation. We're looking for d theta dt, so let's solve for it. D theta dt is going to equal to secant squared of theta. Oops, it should be on the bottom. I should have 1 over 200 secant squared of theta times dy dt. Okay, now dy dt I was given up here was 4. Now, was that increasing or decreasing? The y is that distance the balloon's going up. It's increasing, so we did need that to be positive. So put 4 for the dy dt. Now, instead of having a secant squared on the bottom, I'm going to go ahead and just make that a little simpler on myself. I'm going to make that cosine squared on the top, since cosine and secant are reciprocals. Okay, so now I've got to figure out what the angle is, or at least what cosine squared of theta is. And I want the d theta dt when the t is actually 30. Now notice I don't even have a place to plug in the t. So what I need to do is figure out what this value is going to be after that balloon's been in the air for 30 seconds. Okay, so I need to figure out theta after 30 seconds. Well, to get theta, I could use a trig function, but let's fill in what would this side be 30 seconds later. Well, after 30 seconds, this is going up 4 meters per second. This side's going to be 120 meters. And I know this side is 200, so I can use a trig ratio to know that tangent of theta is going to equal to 120 over 200 at that given point in time, which is equal to, let's see, if I divide both of those by 40, I'm going to get 3 over 5. Okay, so 3/5. Well, if tangent of theta is 3/5, I need to know what secant of theta is, cosine of theta. Tangent is 3/5, but cosine, okay, 3 over 5. This side would end up being the square root of 5 squared plus thus 3 squared. So that's 25 plus 9 will be 34. Okay. Cosine of theta, see, I'm doing this without having to find my angle theta. Cosine of theta then is going to equal to 5 over the square root of 34. Okay, so now I can put that in for my value. So I have cosine of theta squared, so I'm going to have 25 over 34. I'm just filling in right here. I'm putting this in place of the cosine. And then I have over 200. The rate of change is 4. And now that comes out to be 0.015 radians per second. Now you could have gone ahead and found the theta and then plug it in and found it that way also.